Good morning, and thank you for joining today's broadcast titled Intelligent Session Stores with Microservices. Our presenter today is Kyle Davis, Technical Product Marketing Manager at Redis Labs. Today, this broadcast, you will learn how to create session storage microservices in Node.js and Redis that can go beyond simple storage into powerful and compact probabilistic data collection and serving. Today's broadcast is being recorded and all attendees are in listen-only mode. During this broadcast, we will be taking questions. You can post your questions using the question and answer module in the communications panel. Your questions will be answered in the order they are received. Following today's broadcast, an email with a link to the recording will be sent to you for future viewing and share with your workmates. At this time, I'll turn the broadcast over to Kyle. Kyle, take it away.
Thanks, Sharon. Hi, everybody. Today we'll be talking about session stores and how to make them more intelligent with microservices. It's a great topic that I've been talking quite a bit about, presented this at other conferences, and I'm glad to share it with the world through this webinar today. So before I dive into all the great content you came here for, let's talk a little bit about my favorite subject, which is me. I'm the Technical Marketing Manager at Redis Labs. I'm a longtime Node.js developer. I've been doing that for, gosh, close to 7 years now. I'm a longtime user of Redis. I've been using Redis since about 2012. And I'm based out of Edmonton, Alberta, Canada. So that's me on the right. You can see what I look like. This was actually taken at RedisConf that just ended last week. So this is a very current picture. So let's go into the question you might be asking. What is a session store? Maybe you already know. Maybe you're trying to find out more about that. So let's explore that a little bit. I want to explore it through an example. Let's first take a look at some specifics. So a session store is a chunk of data that's connected to one user of a service. Now I'm going to use the term user here. That can be as simple as a visitor to a website or a service, or it can be a proper user with an account, username, password, that sort of thing. So keep that in mind when we're talking about this. So this is somebody or even something that's connected to it. So in the case of an API. Have a session store for that sort of use case as well. It's persisted between the client and server by a token and a cookie. So this cookie is given by the server and stored in the browser or the client. The client sends that cookie back to the server on subsequent requests. The server associates that token with data. It's important to understand that we're not like storing the data on the client. It's just there's a token that identifies. It's a session ID. Okay. It can be other means as well. If we're talking to APIs, it might be some sort of API key or something along those lines. But anyway you slice it, it is a specific bit of data that's stored on the server side that's identified by some session ID, which is in most cases stored in a cookie. It's often the most frequently used data about that user. It's specific to that user only as a matter of definition. And that data should be required for the activity at hand, often for rendering a page or for common use. I'll give a small example of this. When I first started my web development career years and years and years ago, I built this PHP-based reporting tool for a series of retail stores, and I didn't understand how sessions work. How they work. So I built this reporting tool, and it was the most irritating thing in the world to use because you had to supply your username and password on every single page load. So if you wanted to see something that, generate 3 reports, you're putting your username and password in on every single page. In this case, a session would have been useful to persist that identification of the user, who that person is, and what they might have access to, as an example. So if you don't have a session storage, the modern web is not really available to you. So that being said, one thing that I want to talk about is the common and traditional use cases for session stores. This would be username, preferences, name, stateful data. And the way I like to think of this is something that was submitted by the user and is being held by the particular service that you have. And because of that, it's often ephemeral or duplicated data. This information might exist other places as well. So if your session store goes down, well, okay, that's fine. The information is still there. That's in the traditional use cases. Now, we're going to talk about some more advanced use cases today, where things are talking about intelligent use cases. So you have everything on the traditional column, plus you have things like notifications, past behaviors, and particularly today, we're going to talk about the example of content surfacing, which is a really great way of making sure content is always delivered fresh to your users and you're not berating them with something that's not relevant to them. Also, taking past behaviors and storing analytical information. And based on both of those things, you can have personalization as well. Okay, so moving on, let's take a look at this example that I was talking about earlier. In this case, you have a very, very simple web service. You have the internet, which is on the left of the screen. You have a web server, and you have a database. So this is the most simple setup you have that you can have in any type of things. So when people come to the web server from the internet, a page is served based on data from the database. Okay, that works great. That's simple. But you have a problem. You have a good problem. Your traffic grows. And in this case, your web server is having to make more and more connections to the database. And that's a particularly expensive operation for most databases, and indeed for most services in general, is making these connections and keeping them standard. So a database will struggle in this situation. So in that case, you need to solve your problem. Simple enough. So you use what's called on-server session storage. And what this does is you have a small text-based file that is stored on the web server itself that maintains this data that would be stored in the session. So you'll have a session ID, and it'll store a small text file that'll have the keys and values in it. In this case, everything's good. You've restored the performance because you have to make less connections to the database, and everything's stored on the server. And so life's good. However, things don't always stay in this situation. You have some more good problems. Your traffic continues to grow. You have session storage on the server. However, now you need to deploy more web servers because the traffic is overwhelming the web server. So what do you do? In this case, you would launch more web servers. And you have a load balancer between the internet and your web servers. Okay, so the load balancer will go and distribute the connections between the different web servers. And then the web servers will connect to the database. And you only have to have a few connections to the database, so everything's fine, right? Well, this may work in testing, but as you start to deploy it, you're going to come into a problem. This is the problem that happens all the time. So let's say you have a user named Robin. Robin connects to server 1 on her first attempt. And we have that session data stored on a file on the server. We know we can say, hello, Robin. However, next time she's load balanced to a different server, in this case, server 3. And because you're storing it as a text file on the server, you can't supply that session information. Now, there are some other solutions out there. There's what's called sticky sessions. And sticky sessions are an okay solution. However, they're not truly load balanced because in this case, a sticky session would take Robin and only deliver Robin to the same server every single time. That's a problem because you could have a situation where you can have all your users on one server in a given time. So it's not truly stateless. And statelessness is a great opportunity here to make sure that you can always scale your web service. With sticky servers, you have this scaling problem that you're going to have when you move up. Let's say you have the 4th server and you have 1/3 of your user on all 3 of your other servers. Well, then you're still going to have that problem. So there's got to be a better solution to all this. And this is where Redis comes into it. Let's take a look at that. Excuse me. In this case, we have a different topology, and I want to talk about this for just a second. In this case, you have a load balancer between the internet and your web servers, and you're making connection from your web servers to both your database and to Redis. Now, you could, in theory, have a traditional situation where you don't need a microservice, but you might do something more interesting. You're going to want to use a microservice that can handle some more advanced processing and split up your use case. And so you deploy that, and that actually talks to Redis. And then through Redis, your web servers are talking to the microservice. So this way, it's working as a transport layer. So you have a few things that are really here. You have a stateless web server, and you can keep on adding web servers. And because they're completely stateless, you can always serve users, and you can start to scale out horizontally that way. Then you also have your microservice, which you can isolate from the other web servers. And this will enable you to do some more interesting things and do some upgrades and manipulations that you might not be able to do on an active web server, as an example. And then the other thing you have to realize is that you have no single point of failure, because Redis Enterprise has great high availability. And this will enable you to decouple all these things and create a more scalable solution. So I've talked a little bit about Redis. Let's answer that question. What is Redis, right? Redis is an open source in-memory database platform. Many people probably heard of it before. It's great for high performance operational, analytical, or hybrid use cases. Redis Labs, however, the company that I work for, we're the open source home of Redis. We employ Salvatore Sanfilippo, who is the creator of Redis, and he drives our open source development. But we also have Redis Enterprise, which provides an enterprise-grade version of Redis that enables high availability, scaling, and many other things that enterprise customers need. So now that you know that, let's talk about the top differentiators between Redis and other databases. The three top differentiators are performance, simplicity, and extensibility. So let's look at performance. You can dig into these if you'd like, but the key message here is we can provide high volumes of writes and reads, because we're in memory. Those are basically the same cost to our service as far as performance is concerned, at very low latencies. So if we take a look at the chart on the right, if you want to deliver 1 million writes per second, they did this, Google did this particular benchmark, and they said, okay, how many servers will it take to deliver 1 million writes per second? So Cassandra required 300 servers. Couchbase required 50. This is to deliver 1 million writes per second. Redis required 2. So as you can see, 25 and 150 times difference. It's huge. And then if you look at the graph on the left, this is an independent consulting group, Avalon Consulting, created this, and you can see the line chart represents the latency when you're at a very high volume of writes, and the bar graph represents the actual throughput. And as you can see, the difference here is we're providing very low latency at very high throughput. So moving on to the other differentiator, simplicity. If you've not used Redis before, it's an interesting way to take a look at it, is to say, okay, we're not like other databases. We're not a key value store. We're not a relational database. What we use is structures. So in Redis, we have a key, a structure, and a value. And everything descends from that platform. So you have, starting on the upper left, strings that just store plain text stuff. And then you have bitmaps where you can store binary data. We're really great at that. We have bit fields, which enable us to store numbers in units that you're familiar with, unsigned 8-bit, unsigned 10-bit, signed, that sort of thing. Hash maps, which allow you to have key and field and value for each one of those. So you can have a collection of things all bound together under one key. Lists, which are basically linked lists. Sets, which are the classical sets, a group of items with no repeats. Sorted sets, very similar to sets. They have a score associated with each member of a set. Really great for leaderboards. Geospatial indexes, which now enable you to plot points on the Earth and then find things, the distances between those points and other points within radiuses. Hyperlog logs, which are a probabilistic cardinality estimation system. And our newest one, that's right now, it's still in development, but we like to put it on there because it's important for you to know about, is streams. Streams are a structure which enable you to stream data in to Redis and then out as well. This enables you to do great things like time series, IoT data. They're really great matches for streams, as well as stuff like building an entire application on unified log pattern. So all these data structures can be put together to create many different applications. However, you're not limited to these data structures. Let's take a look at extensibility. A few years ago, Redis had the data structures that it had, and you had to create everything based on those. They introduced the modules API, which adds seamless support for additional use cases and data structures. So that means that you have a first-class citizen in Redis that is potentially your own data type and your own commands. So this integrates very deeply in Redis, so you get the same high performance and scalability and high availability. It's written in any systems programming language like C, C++, or Rust. And so you write the module, you integrate it with Redis, and then you can create your own data structure, whatever you need for your particular use case, or you can use the existing ones in different ways and kind of mix and match. So it can be used by anybody. Redis Enterprise modules are a program we have that are tested and certified by Redis Labs, so you can integrate them into our Redis Enterprise product and be ensured that it'll have the same great stability that you would notice from Redis itself. This is really key because it turns Redis away from just being, a place to store things in these set structures. It turns it into a multi-model database. We've turned it into a graph database. We've turned it into a time series database. We've turned it into a high-performance search engine and more. So you have a truly extensible database platform. You can look at Redis with modules. So with Redis Enterprise, which is the enterprise-grade deployment, we have 3 models. We have a cloud, which is fully managed and serverless. It's hosted on basically any cloud out there: AWS, Azure, GCP, SoftLayer, Heroku, Cloud Foundry, OpenShift. And then we have VPC, which is a fully managed service that is based on your particular infrastructure that you set aside. We manage it for you. And then we have software, where if you want to have an on-premises deployment or you want to have full control over everything, then we provide you the license for the software, and then you install it, and we can help you with that, but certainly you can do whatever you want to with it. Now, if you see, there's RAM and Flash at the bottom of these 3 deployments. What's interesting about this is Redis is traditionally known as an in-memory database, and indeed we are. However, we have the ability to extend it into Flash. What that means is we can take Flash memory, an SSD, essentially, and then you can extend Redis into it to create an extension of RAM. So this means that you're no longer bound by the DRAM that's available on your server. So with that, you can have huge data sets all in Redis, and the hot values will be stored in DRAM, in the fastest storage available, and then the colder values will be automatically shuffled into Flash. So this way you can have huge data sets and not have to worry about, tiering it yourself. So that's Redis Enterprise. Let's take a look at the session microservice, which is what we're really here to talk about today. And you might be asking, why would you have a microservice for sessions? Sessions are considered to be an important but relatively simplistic part of building a service in the web or for any type of other device. Well, let's take a look at that. There's a few reasons. The first thing I want to talk about is that they abstract function from one particular code base. I want to be clear about this, though, before we get into everything. For simple and traditional use cases, if you're just trying to store, like somebody's username and password, you don't need a microservice. You can certainly use Redis. Redis is a great database for that. But in this case, we're going to do something a little bit more extensive with it. So we're going to use a microservice for it. And as you might imagine, doing something more extensive with a session store, your complexity is going to grow. And this allows you to decouple the session storage from the serving layer. So I know we've probably all been here before. When you amass a large group of developers, one problem kind of arises. You have these kind of wars of one person saying, no, I want to work in this language. No, that language is garbage. You should work in this language. And it becomes almost a hostile situation, which is a little bit weird when you really abstract away the scope of things. But one group may want to work in Rust. One group may want to work in .NET. One group may want to work in Node.js. And the microservices architecture allows you to do that. So you can take something and you can have a serving layer built in one language, and you can have an entirely different language as your, let's say, microservices for your session store. And this allows for people to be happy. A happy developer is a productive developer. And as well, it can reduce the overall complexity of the entire code base, right? So you look at a code base and you say, okay, if you have this huge code base because you're using something that maybe is not particularly suited for it, or you have somebody that's not particularly good at that particular language, then you're going to have some pretty garbagey code, and no one wants that, right? So what we can do is we can have a very simple microservice and a more simple serving layer, and they're independent of each other. So it increases focus. So you can just focus on whatever you want to do in your microservice, and that team can work on it independently from the team that's working on maybe the serving layer. And then you can also be a little bit more agile about things. So your serving layer may move a little slower, or your microservice group might move a little slower. Because they're not coupled, it's really great. The other thing to look at is performance and scalability. We're Redis Labs. We're obsessed with performance. And if you have code that's devoted to one functional area, you can make sure and isolate it into a microservice, and so it doesn't drag down a whole monolith. You may have seen before big code bases, and it has one, let's say function that's 100 lines of code that's really bad. And so in that case, the whole monolith is probably going to be drugged down by that. If you have it isolated in a microservice, you can then make sure and isolate those particular areas and maybe iterate on that a little bit more, and it won't have as big of an effect. You can also have particular hardware and infrastructure devoted to particular parts of the operational sequence. Now, additionally, that hardware infrastructure may be tailored to that specific use case. As an example, you may have a situation where you're doing something quite computationally complex in your serving layer or maybe in your microservice. In that case, you might want to devote more CPU resources. So if you're in an AWS environment, you might have something that has more, let's say, cores available for it, for that particular part. Or you have something on the other end that is very network heavy. In that case, you want to have something with a very high-speed network card. And so in this case, you don't have to go in and say, I just need the biggest instance available. You can say, okay, I need an instance that looks like this for this particular part of my infrastructure, an instance that looks like that for a different part. On top of this, requests to microservices can be both synchronous, or can be either synchronous or parallel. In this case, this will decrease the time that it takes to respond. So when you have that, you might have something that says, okay, I need to do this part of the, let's say you're sending it out to the microservice, but it doesn't really matter to your particular use case that you know the results of that, right? So then you can say, okay, in this case, I'm just going to let that kind of say, yes, the only acknowledgement is that I didn't have an error when it's sent out. And then, okay, it's going to handle it on a different hardware, maybe in a different part of your data center or a different part of a cloud, maybe even a different cloud. And your serving layer is just going to keep on checking. So in this case, you can really fine-grain control things, and you can really make sure that you're not having any problems that might bubble up and risk your performance budget. So the other thing is microservices can increase the overall uptime and fault tolerance of your given system. So microservices, because they do involve the serving layer intrinsically, you have to build in fault tolerance. This is just a requirement anytime you make a request beyond the next line of code in your particular code base. So in that, you're designing your system to be more fault tolerant just out of the box, right? The other thing to look at is isolation, and we've talked a little bit about this before, but I think it's an important point. One service bringing down other services can be made impossible. So if you've isolated that one microservice and say, okay, I built the rest of my system to rely on it in a fault-tolerant way, let's say that data center catches on fire. Well, okay, that's a terrible thing to happen, but in this case, it's isolated from the rest of the service. So you have this ability to maybe degrade rather than fall hard. That's something we always want to avoid. We just don't want a system that doesn't respond. So a degraded service is much better than a dead service. So getting into it, let's talk a little bit about how this might look. There's two different flows. There's a critical flow and a non-critical flow. In this case, we're going to record page views. So we're going to have something that happens on every single page view. Now, on this first line here, it says pattern subscribe to anything with ss::page view and the little asterisks. Effectively, what we're doing here, that's happened when this microservice starts. Okay, let's jump over to the left side of the serving layer, and you get an HTTP request that you're going to respond to, right? Since this is going to happen on every single page view, what we're going to do is publish a message using PubSub in Redis, using two unique identifiers. So in this case, the channel is going to be based on a session ID and then a unique request ID. So if you look at this from a long view, you'll have many of these request IDs for every single time someone touches a web resource that you're recording. Maybe something that you're serving statically, you don't worry about. So that's published. Now, publishing in Redis is a very, very cheap operation. It's what's called O1 in time complexity. And it doesn't take any time to do. It's very, very simple. It will execute in far less than a millisecond in most cases. So that's published. And then what's going to happen is we're just going to publish that and say, okay, we got acknowledgement that it published successfully. And then we're going to go ahead and render the route and then close connection. So that's being sent back to the user. The user doesn't know anything else is going on. However, simultaneous to things being rendered, we get the message from the serving layer. We start analytical processing. And then we end the analytical processing, and then we post back to this list, right? And the important thing here to know is this list is something that's ephemeral. So this list will self-expire in 500 milliseconds. So in this case, it's kind of like a tree falling in the woods. No one's here to listen for the tree falling in the woods or the message being published to this list, so it doesn't really exist for all intents and purposes. So in this case, what we're doing is we're making sure that we're having two parallel flows on two separate machines so they don't interfere with each other. So this is going to make sure the serving layer is sending things out as quickly as possible. Okay? So moving on, let's talk about the critical flow. In this case, what we're doing, we're going to render the page that later on in this process based on the data for the microservice. So as before, when the session service started, we've subscribed to this particular pattern. This is going to seem very familiar for the first couple of rows, or excuse me, rows. So if we look at the serving column layer, we get the HTTP request as normal, and we publish just like we did before. And then things start to change. So we're going to use what's called a blocking list in Redis. So the command for that is blpop. And what that means is we're going to wait for any information to come to that particular list. So that means we're going to have this time where what we call the client is blocked. Now this means that only that particular layer. Now, in an example like Node.js, which is single-threaded but is asynchronous, this means that it's just going to be waiting for the network connection to respond back. Okay, so in this case, we're going to pop over to the right side, and it says get the message from the serving layer. So that message comes in, which was published previously. We start our analytical processing. We end our analytical processing. Then after that process is over, we're going to post that message, that list rather, that we were waiting on the other side. So that's going to then trigger the serving layer to come back alive for that particular request, get the response to the blocking command, and then we're going to render the route and close the connection. So in this case, it's synchronous. So as you can see, what we're doing with all this is we're actually being able to go through and process, in this case, in a way that is like a waterfall. So one depends on another. So that being said, let's go ahead and take a look at a demo. I'm going to switch over here. Okay, and everybody can see my screen. And I have this little application. I have the source code to this available. And this is a demo source. This is like an e-commerce type example. And this demo is actually much more full-featured than this. So I encourage you to take a look at all that we're doing with it. But I just want to highlight one particular area. And that's the featured products category. Okay. So in this case, what we're going to do is, let's say that we have an e-commerce store and someone added a TV to their shopping cart or a TV mount as an example. You don't want to show that again. They've already bought the product, so it's irrelevant to show it. So I'm going to go ahead and click on this value. And it says, thank you for adding a TV. This is all dummy information. I'm going to confirm my purchase. Everything's good. Okay. Now, if we look back here, the featured products, again, is missing that one piece. Now, that in itself is not that amazing. But individually, when we look at this, this is a scalable solution that we can have for many, many more items than this. And this just a couple of things to show you how it works. So we confirm our purchase again, and then we go back home, and we notice that whole section is gone, right? So these are an example of critical flows. And every time we're doing this, I'm basically looking and saying, okay, was that particular path, in this case, it was right here, if you can see that, /added/TV mount, if it's ever been visited before. And so in this case, I'm making sure that that's triggering adding a particular item to what's called a Bloom filter. And we'll talk about how that works in just a second. So as you can see, it's not there. And if I was to create a new session, so let's do that actually, copy that. I'm gonna create a new incognito window, which should basically reset the session. So we're in a new session ID. And we see that's back, right? So I could go in and just see this part, confirm the purchase, go home, and you can see that it's gone again, okay? And here it is running in the background just on my particular machine. So we could just for this example. So let's switch back over to the presentation. Here we go. And then the presentation, let's look at how it all works. I mentioned the Bloom filter before. Bloom filter tests for presence, and it's a probabilistic data structure. So in this, what we're going to have to do when we add an item to it is we're going to run it through a hash function. A hash function will generate a unique set of bits bits for a particular value. So you input a string value, and then it's going to output particular bits. So we're going to sample those bits, and then we're going to set them into a particular bit field, okay? And that could be of any particular size, but let's say you have a fixed size for this example. So let's take a look at this part up here where we've got this little diagram up in the upper right. In this case, we have X, Y, and Z, and those are all sampled. And you can see that we flip from a 0 to a 1 for each one of those. So the blue line represents X, the purple line represents Y, and the red line is represented by Z. So as we look at this, we can see, okay, those have all been set, so we know what they look like. Now, we're going to test for presence in this. And I'm going to use W. If you look at W, it's on the bottom. It's got the gray line. So there's going to be overlap here. So some of these values, some of these little bits are already set to 1, and that's okay. A Bloom filter, as soon as it hits a 0 and it's hashing values, it knows that that's never been in the system before. And it can, with certainty, return that, yes, I've never been added to this value's never been added to the Bloom filter. So with that, there's some properties you have to look at. False negatives are never possible. So in this case, you have W. We know for certain that it has never been added before, because if it had been added, that last 0 on the far right, where the little gray line's pointing, would have been flipped to a 1. However, false positives are possible, but they're controllable in most situations. I'll get to that in just a second. The advantages of this is that it's mere bits, not bytes, but bits per item. So you can have a huge number of values in one Bloom filter, and the size may not change. As an example, you can have 1,000 items in a Bloom filter or 10,000 items in the Bloom filter, and given the proper setup, that may be the same actual storage in your database. So really amazing data structure. And I like to say it's like the TARDIS. If you watch Doctor Who, it's bigger on the inside than the outside. But there's two particular things you can do with a Bloom filter. You can either add an item to a Bloom filter or check if it exists. So we covered both of those things, but that's the only two things you can do. You can't say, give me all the items in a Bloom filter. They don't exist. Only the bits that have been set based on the hash value for each item has been set. And then if we look at it, where is it available? This is a common data structure. It's available in lots of places. However, in the Redis world, we have it in two different ways. We have it in the rebloom module, which is, like we talked about in the extensibility section, a module that integrates with Redis. Or if you don't want to use that, and let's say that you're using our Redis Cloud service, which right now does not have the rebloom module integrated with it, you can implement it yourself using the inbuilt bitfields command. So how does this all come together? I've introduced a probabilistic data structure to you. I've gone in and talked about how the flow works. Let's talk about the actual use case of the pattern that we're using. So backing up a little bit, the traditional content surfacing pattern might be, okay, you have a particular set of items that you want to show to all your users, and you store that set of items that you want to store to all your users in a table, and then you just serve that out to every single user. Okay, this is very basic, and you've probably done something like this and say, these are my featured articles or featured items in a site or something along those lines. However, this has got some challenges. So you're going to serve content multiple times because you're relying on a handpicked or rotated set of items. And the freshness is linked to this manual curatorial or some sort of time-based interval. So it's not really going to give you much customizability or real-time advantages to it. It's pretty basic. It'll work for some cases, but you're going to waste that featured area on things that many times people have already seen. So let's take a look at a little bit more advanced but not smart way of doing this. So you have a batch process that builds a list of content for each user. So you have 1 million users in your web service, and you would say, okay, we know that user A likes item 1, 2, and 3, items 1, 2, and 3, and then you store that in a database table. And then you serve that out to a particular user, and you rotate that. Okay, so that's better, but it has some challenges as well. It's not real time, so you still have this batch process that you might run every hours, days, whatever. And you're still going to serve content multiple times. It's going to be maybe a little bit more tailored based on something you've already set up, but that could be even quite difficult to build. And the other thing is this is uncacheable, right? So you're going to have a hit to your database every time you show this, right? You want to make sure that you're showing that for a particular user. And it's going to be difficult to scale because of this, right? So you're hitting your main database every single time. And with this per user in your database is not a great pattern. and it would be difficult to go through any scale and somehow insert this into their individual sessions. That's not usually how sessions work. So let's talk about a more modern and intelligent way of managing this particular problem. So you have a middleware that adds each item that's read into a Bloom filter when it's viewed, right? So like I was doing before, I added TV mount as an example. You have a featured list of content that you want to show to every user. This is your featured content list. However, the items are checked versus a Bloom filter on the fly versus data in the session store. Because the session store is holding all the pages that someone has viewed, we can then go and say, okay, is something in the featured list available in the Bloom filter? So let's take a look at some of the advantages here. You basically have a situation where you have no database hits. So this is all directly managed inside the session store. The featured content is highly cacheable. So in this case, you can have something that either caches into Redis or particularly onto your web servers or something along those lines, and you never have to hit your database to do this, which is a real big advantage, especially as you scale. It will not show content multiple times if you've already read it. This is a huge advantage, as if you've read something or you bought an item, you probably don't need to feature that again. It has an absolutely infinitesimal amount of storage required, even at scale, because Bloom filters are so storage efficient. You can have a Bloom filter for every single user that has stored every page they've ever visited, even on a large site, in a probabilistic way, and you can compare that with the featured content list. So you have a smaller amount of data that goes back and forth. And the freshness can be achieved without this curatorial process, right? So even though you may have your featured content list, you keep that with a very large number, a very large cardinality, and then you just rely on your Bloom filter to continually check that and make sure that you're not showing the same thing over and over again to users. And it's real time, right? So you're recording the activity as it happens. So when somebody clicks on something, let's say a page, and they go and see this featured list, it's immediate. And so you have the ability of showing something new every time and keeping users engaged. So that all might be interesting to you, but let's take a look at maybe visually how you might represent this. So on the left-hand side, we have our content list. Let's say we have 6 items in our featured content list, okay? And then the middle part, this fuzzy, which I make it fuzzy intentionally, box to represent probability, right? This is our Bloom filter, okay? And I would want to say that I'm using checks and X's here, which is a little bit confusing because we're inverting these. So in the case that there's a check, that means that it's not in the Bloom filter. X means that it has already been there. So in this case, the Bloom filter says, okay, we've checked all these 6 items in the Bloom filter, and item 2, 4, and 6 have already been seen. So we're not going to serve those items out. But items 1, 2, and 3 have never been seen. So let's say we go ahead and we browse item 1 because that looks interesting to us. So I'm going to go in and I'm going to add that to the Bloom filter. Now it's going to turn into an X, and we're not going to see content 1 on subsequent loads. So that's how this all works. Let's enter a time where we can talk about questions. I have a whole list of questions that have been coming in. And so I'll just start out with one that we've got at this point. It's regarding what languages can use this pattern. It's an important question. So there's a couple of things that you can look at. Redis is really great because it has a high number of clients available in different languages, right? Almost any major programming language, somebody has written a Redis client for us. So that's great. So you can basically, anything that has a Redis client can support writing your microservice in that, because you're not actually interfacing with the actual direct web traffic. You're only interfacing with Redis itself. So in this case, you could write it in any number of languages. Personally, in my testing when I developed this particular piece of code, I was actually able to, I wrote a mock web service in Rust, and I wrote one in Python. But you certainly can use whatever language you're comfortable with, Elixir or something along those lines. Whatever your team uses, Java, certainly, PHP would be a good choice for some cases. But then we look at the serving layer. This pattern requires that you use the middleware system, which middlewares are where you have kind of a number of steps that waterfall before you serve something. In that case, you'd have to look at the serving frameworks more than the languages itself. In PHP, something like Laravel would have that ability to do that. Certainly in Node.js, I'm using Express in the demo code, which, by the way, I'll give a link to in just a moment. And almost every modern web framework has the ability to have this kind of a middleware pattern. It's very popular. So those things are really easy ways to use this. So as you can see in the example code, I built it all in Node.js. That's just the language I'm comfortable with. But certainly you could mix and match different languages together based on your particular set of talent that you have and whatever you feel like is really great for the process that you have. Okay, so what other things can you do with intelligent session stores? So intelligent session stores, like I said, it's kind of an overarching title. With intelligent session stores, you can add other things as well besides just this kind of Bloom filter thing. It's a great match for anything that you want to do some more extensive processing on. One of those things is obviously analytics. Analytics are a huge thing these days, and customized analytics are really important for gathering information that might power a particular business use case. So in the demo code, as an example, one thing that I've done is I've looked at taking your activity as people go in and they're running a particular, they're being active over a series of minutes. You can actually go and flip bits in Redis and create a really compact way of looking at the activity of a user over time. So you have a kind of a pseudo time series system that you can build really compactly. That might be really complicated to implement in a traditional situation where you're just integrating directly with your web framework. But in the situation where you have the microservice, it'd be very trivial to do because you can store that all there and not have to worry about throwing the complications in. Another thing you can do is work on notifications. Notifications can be a particularly complex topic to deal with, and this is something actually I did cover as well in the example code. You can use a Bloom filter pattern again to manage if you've seen notifications or not. This can vastly reduce your workload on your database because that could be really tricky if you have a high volume of users coming in at one time. So that's just a couple different things you can do with intelligent session stores. But the one thing I want to let you know about is really the sky is the limit when you start thinking about decoupling the session store from the serving layer of your database. That way you can have a really customized solution for your particular use cases. Okay, so we got another question that came in. How do you form a Redis cluster with Flash data in case of failure? Okay, so one thing Flash is important to understand here is Flash is not used for durability. Flash is used for an extension of your storage, right? So in that case, it's relatively transparent to the cluster that it's using Flash, right? So in most cases, you'll have a primary and secondary or master and slave topology, and you both have Flash on both of those situations. Another interesting thing that you can do is you can actually use an active passive method to distribute your data. So in case of disaster recovery, so you may have your primary database that runs all on RAM as an example, and then you can have a really big database that uses Flash for disaster recovery, and then use in-memory replication, which is able in Redis Enterprise to take those clusters and replicate those clusters. So in that case, what you would do, let's say you have a total disaster and your data center catches fire, right? The worst thing that could possibly happen. So you have in the second data center, you have that disaster recovery node, and then you would just rebuild your cluster as you would normally, and you would use that and use active passive replication in the other direction to repopulate that. So in that case, what's going to happen is the data is going to flow in, and as the data flows in, it will start marshaling between the Flash and the RAM to achieve your same replication as you did before. Internally, Redis keeps actually a little count of the activity that's available in those particular keys. So that would actually be replicated as well. This metadata would be replicated because it is part of the keys, right? So that being said, you can really make sure that you have that Flash cluster up and running. Okay, I think that's all the questions that we have for today. So I'm gonna let you out a little bit early, but I do want to let you know all the source code is available to this. I put a bit.ly link up here. It's redis-sessions-store. And you can take a look at this. There's two services here. There's a microservice and then the serving layer. Of course, this is just designed for demo code, so you can see how it works. When you want to deploy it, you're going to want to have a little bit more to it than that. The one thing to keep in mind is the session store can be sharded out, actually, and so you can have multiple session stores running and multiple services running as well. So that's all we have for today, and thank you very much, and I'll throw it out to Sharon to close it out.
Hey, thanks, Kyle. Hey, great topic with quite a few terrific questions. So we're at the end of another broadcast. An email with a link to the recording will be sent to you for future viewing, as well as to share with your co-mates. Join us on our next broadcast. Go to redislabs.com/webinars and check out what's on tap and register. So until next time.